Okay, now let's look at a different scenario that we have a load word or store word. So there are some cases that use labels. So for example, we had something like load word S1, and then we would give it, for example, array. So this was a case that we are using a label. So I briefly hinted about this before, but basically there are no labels in machine language. All the label is, so let's say you have, this is your code, and at some point you are putting this array. So all the label is doing, it's basically marking this location. So if this has memory addresses, so let's say, for example, 1001, 0000, and then it's going, and then 1001, 0, let's say 008. So like this is a different address. So when you put the label here, it's gonna just mark this location. Or what I mean is that when it's trying to basically assemble this, whenever it reaches to somewhere that you're using this label, it's gonna look up what is this address on the memory, and it's gonna just replace that. So it's just gonna take this number and put it here. So it's just something for you, for the programmer that is using Mars, or you are using basically assembly to be more simple to program, because you don't know what this address gonna be at the time that you are coding. But so you can just put a label, and then this label gonna be replaced with that actual address. So that's how the labels work, and we're gonna see examples of that. So we said for so here we're gonna see an example of actually offsets first. So when you are doing a load word, so first of all, that's the I format. That means you have 16 bits here, right? So that 16 bits here can take a number. So let's look at this instruction specifically. So we said there are different cases that we had, right? So this having a label was one case for load word. Here we are using a register and the offset. So for example, load word S0, 5, and then S1. And 5 is not a good number. Let's put, for example, 8, because it has to be memory aligned. So we said this is one type of load word that is valid. And how that works is basically we are going to calculate this address. So normally if, let's say, S0 was 010000, so this was S0, sorry, S1, and you only had load word S0, S1, so you didn't have this offset of 8. You are going to read from this memory location directly. But when you have that offset, we said that this offset is going to be added to this location, and then we're going to read from that. So in this example, we would be actually doing +8, and we would read from 1001, 0008. So that would be the address that we would actually read from. So here we have that explaining the same thing. So this address is actually equal to RB, so that's the content of that register, plus our I, and that I is going to be signed extend to 32 bits. So as we saw, that's only 16 bits. So how do we represent this in the I format? So we have this code here. So that's our operation code or opcode, and that's basically telling the processor that I'm doing a load word. So this load word and that, so these are the same thing. This is how we write it, and this is kind of the translation or the code for load word for the processor. And then we have two registers. We have RT and RB. So each of this is 5 bits and 5 bits. So then we have those. And then we have 16-bit I for this offset that we have there. So that I is going to be in this part, basically on the lower part of the instruction. And that's going to be 16-bit. So not so bad. Now let's look at example that you are given this instruction. So you have a load word, and it's using the offset format, and you want to basically convert this to assembly. So if you can look up the table and you can basically fill this, so nothing new here as part of these registers, you can basically look at load word, and you want to say, let's actually clear this. And so load word, if we go to there's a table further in the slides. Here we have load word, and you see all this pattern. So you have the 16 eyes here, you have 5 for this register and 5 for that register inside the parentheses. And you see that the code is 1000, so 3 zeros and 1 1. So that is basically what we have here. So 1000, 1 1. So that's basically the code for load word. And then this one is going to be the stack pointer. So you have to look up what is the number. So maybe it's I don't know, maybe like 30 or something like that. And then you're going to look at the S0. So maybe that's, I'm thinking like 16, maybe. So you convert those into binary, whatever that number is. And you get that there. So you get this part, we get this part, and we got the load word. So this is the remaining part, that is the I. So that is kind of the new part here. So how do we convert this to the 16-bit? So first thing is -4. So that's again goes to kind of the first chapter. So how do we represent -4 in binary? And we said that all the MIPS that we are dealing with here, so all that we are dealing, it's actually in 2 complement system. So there is 2C, everything that we are dealing with. So a negative number is going to be represented in 2 complement number. So how do we do that? So let's kind of like a flashback or looking back. So we said 4. So first step was to convert that to binary. And what is 4 in binary? Well, 4 is 2 to the power of 2, so it's 1 0 0. So that's 4 in binary as a positive number. And we said that we want to, since it's a negative, so we have to have, since it is a positive number, I don't want this last one to be a 1. So I'm going to pad this with 0. So 4 is basically 0 1 0 0. And if you want to convert that back, it's going to be indexed 0 1 2. So it's going to be 2 to the power of 2 equal to 4. So this is 4. The next step was to basically flip this. So convert it to complement. So we said we're going to flip. So flip, we're going to get 1 0 1 1. And then the next step was to add 1. So when you add 1 to this one, you're going to get here 0, you're going to get a carry. So 1 plus 1, again, you get a 0. You're going to get a carry 1. And then you're going to get 1. And this one just going to drop. So now that is your number in, basically that is representing -4 in 2C. So, and you can try that if you want to kind of make sure. You can try that to basically convert this one to decimal and to see what you get. So you're going to get -4. And doing that is going to be the same thing. Plus you add 1 again, and then you flip, and then you convert back to decimal, and then that's basically your number. You just add the negative sign. Okay, so here you have that -4 in 2 complements. So we are almost there. The only last thing to do here is that this is a 16-bit I. So you have to, so if you just put here zeros, and then you put this number 1 1 0 0, this is gonna look like a positive number, because if somebody gives you, let me actually write it. If somebody gives you this number, so this is zeros, 2, 3, 4, and then 1, 2, 3, 4. So if somebody gives this number and tells you convert this number, looking at this, it looks like a positive number because this last one is a 0. So you probably gonna do 0, 1, 2, 3. So you say it is 2 to the 3 plus 2 to the 2. That's 8 plus 4 and equal 12. So you say it is 12. But that's not what we have here. We have -4. And the reason is that you have to sign extend. So whenever you're dealing with a negative number, like here, -4, when you're representing that in a larger space than the number, so here you have 4 bits, but here you have 16 bits. So in order to put this number, the 4-bit number here, you have to sign extend. Otherwise, you're going to lose the value. So if you sign extend to 16-bit, basically you're going to get this one. And sign extend is nothing but copying this sign bit as many times as you need to fill the space. So if it's a 1, you're going to put so many 1s. If it's a 0, you're going to fill that with 0s. So basically, that's it. So here we have this assembly, and this is the machine code for that. Yeah, and the only tricky part is basically this -4. If it was a positive, it would be basically more straightforward.